Welcome, everyone. Thanks for joining us. We'll get started. I know that some people will still be coming on, but we can get some of the preliminaries out of the way. This is the second of the Livermore Lab Foundation's 4-part summer speaker series, and we're featuring a variety of past and present leaders from Lawrence Livermore National Laboratory. I'm Donna Crawford, co-founder and chair of the Livermore Lab Foundation. We are an independent nonprofit organization and philanthropic partner of the lab. We're dedicated to advancing science and inspiring future generations of scientists and engineers. We'd like to ask everyone to please remain muted during today's talk and perhaps even turn your video off until the end, when hopefully we'll have time for questions. And just also a note, we are recording today's event, and this entire series will be available on our YouTube channel later this summer. So as you all know, this is a milestone year for the lab as it celebrates 70 years of advancing science and technology on a mission. Today, we are very pleased to bring you Igniting Stars on Earth with speaker Tammy Ma. We've asked a very special guest to introduce Tammy today. Kim Budil is the 13th director of the lab and the first woman to assume this role. Kim sets the strategic vision for the lab and ensures the successful execution of programs and operations to advance science and technology for the nation and to maintain an outstanding and diverse workforce. Here's Kim.
Hello, I'm Kim Budil, Director of Lawrence Livermore National Laboratory. At the lab, we use cutting-edge science and technology to tackle the biggest problems facing the nation and the world today. Few challenges are as big and important as the need to provide clean energy sources for a growing and advancing world. The National Ignition Facility, or NIF, is the world's largest and most energetic laser system. It was built to pursue fusion ignition in the laboratory and create the most extreme states of matter in the universe, just like those found inside stars and planets. Dr. Tammy Ma and her team perform experiments studying inertial confinement fusion, seeking to recreate miniature stars on Earth at the NIF. This work is a necessary first step toward harnessing these fusion reactions as a potential source of energy. Tammy is a very accomplished scientist, leading our efforts to advance inertial fusion energy and performing award-winning scientific research, making her a rock star here at the lab and in the community. I hope you enjoy her presentation. Be sure to listen for the many ways her experiments are paving the way for clean, near-limitless energy. Thank you for your attention. And now, back to you, Sally.
So I'm not Sally, as you know. We recorded the introductions thinking Sally Allen, our foundation executive director, would be the MC, but Sally couldn't join us today, so I'm subbing. We are very pleased to have Kim set the tone for today's talk and are delighted to welcome Tammy Ma. Dr. Tammy Ma is an experimental plasma physicist in inertial confinement fusion, or ICF, and high energy density physics at the National Ignition Facility, NIF. Tammy graduated from Caltech in 2005 with a bachelor's degree in aerospace engineering, then received her master's in 2008 and PhD in 2010, both from the University of California, San Diego. She subsequently completed a postdoc at Livermore Lab before transitioning to a staff scientist in 2012. She now leads a number of the fusion experiments at NIF and currently heads the X-ray analysis group for the ICF program. Tammy has authored or co-authored over 135 journal publications and is strongly committed to education and scientific outreach. Among many other honors, Tammy recently received the Presidential Early Career Award for Science and Engineering, the highest honor bestowed by the United States government on science and engineering professionals in the early stages of their independent research careers. Not only are we delighted to have Tammy normally, but she's actually on vacation in Glacier National Park. So we are especially fortunate that she is joining us. Welcome, Tammy.
Thank you so much, Donna, and thank you, Livermore Foundation. Yeah, as you can see behind me, I'm sitting in Waterton National Park, which is just the northern end of Glacier. This is the part that belongs to Canada, and this is my first time here. It is amazing. I'm here with my family, and I apologize that I'm not in my office to give this talk. It's sometimes difficult to balance, work-life balance and juggle a family schedule too. That's why I'm sitting in the park today. But anyways, I am going to turn off my video now and share screen. We're going to save a little bandwidth that way. But thank you everybody so much for joining. I'm very excited to get to share with you some of our recent results from the National Ignition Facility and the path it leads towards a clean energy future with inertial fusion energy. Can someone confirm for me that you're seeing the full screen of the slides?
All good.
Okay,
Yes.
perfect. Thank you so much. All right. So let me start by saying that this work builds on decades of research by an incredible team across Lawrence Livermore National Lab and the wider community. So it is my sincere pleasure to get to share the results on behalf of this enormous team. And on the right, you see some of the logos of our main collaborators that we've worked with over several decades, both domestically and internationally. So it's with this magnitude of big science projects, we necessarily need a lot of really great people working together. Okay, so let's start by laying the foundations, the background for why we are so interested in fusion. Here is a plot of world energy consumption projected from 1990 through to 2040. And it is expected that worldwide energy consumption is projected to increase 33% by the year 2040. So in less than 20 years from now, we have to find a way to provide 33% more energy than we currently use today. That really is an enormous number. So it is instructive then to take a look at how we provide for our energy needs today. These logos that you see down here at the bottom are representative of different types of energy resources, and their size is proportional to the energy it actually provides. So you can see that today, coal, oil, and natural gas still provide the majority of our energy. And of course, we know coal, oil, and natural gas are carbon-based energy sources. They have to be dug out of the earth, which means that they are not renewable. It is exhaustible. And furthermore, they contribute to global warming. Now on the left, you see there wind and solar. Wind and solar are amazing. They're great, clean, renewable energy sources. However, last year, 2021, it was a big deal. We were only able to provide 10% of the world's energy needs, electricity needs through wind and solar. So you can see there's still a pretty large gap that needs to be filled. So the question is there another solution, right? Could we build a miniature sun here on Earth to provide significant carbon-free energy for humankind? Well, the sun and the stars are powered by fusion, and fusion conceptually is very simple, actually. You take a light element, in our case, we're interested in hydrogen, actually isotopes of hydrogen, deuterium and tritium, so it's heavy hydrogen. If you can slam those atoms together with enough heat and with enough density through the fusion process, you generate a helium nucleus on the other side. This is an alpha particle and a neutron and a huge amount of energy. Well, how does that actually work? If you were to weigh the reactants in your reaction, deuterium and tritium, they weigh a certain amount, and then through fusion, your products on the other side actually weigh a little bit less. So if you take that small differential in mass, stick that into an equation we all know very well, E equals mc squared. You take that m, you multiply it by c, the speed of light squared, and we know the speed of light is a huge, huge number. You actually get a huge amount of energy out. So the reaction that we're interested in, the D plus T yields an alpha plus a neutron. The Q of fusion that we have there, which is the exothermic energy released through this reaction, is about 3.3 times 10 to 11 joules per gram. What does that mean? In a single gram of fusion fuel, that's equivalent to the amount of energy we have in 100 barrels of oil. So that is the potential of fusion energy. Now, fusion energy is actually attractive for many reasons. First of all, it is inherently safe. What we mean by that is you do need to first deliver quite a lot of energy into your system to get fusion going. So if you ever want to stop a fusion reaction, it's very easy. You just cut off the initial energy source. So you don't have to worry about runaway like you might with fission. It's entirely carbon free. You saw in that equation, there's no carbon anywhere in there. It's sustainable. We know how to obtain the fusion fuel that we need without damaging the environment. In fact, deuterium is actually naturally occurring in seawater, 1 in every 10,000 particles. Instead of H2O, it's D2O. And then tritium, we know how to breed from lithium. Baseload, it's envisioned that a fusion power plant would be a gigawatt scale plant able to feed cities about the size of San Francisco. Furthermore, fusion is entirely able to meet demand when you need it. So you don't have to wait for the sun to shine or the wind to blow. You can turn fusion up and down to meet demand. Energy security, if we can demonstrate fusion to be a viable energy source, no longer will we be reliant on foreign oil imports. And finally, there's no geologic storage. There's no high level of your waste associated with fusion. So that's why it's so exciting and interesting. So there are at least 3 ways to achieve nuclear fusion. Some of these might already be fairly familiar to you. There's gravitational confinement, so what the sun does. Magnetic confinement, as in large tokamaks or the ITER project that you might have heard of in the south of France. And then inertial confinement, primarily using lasers. What we'll be talking about today. So what we mean with each of these 3 different approaches is they reside in very different temperature and density parameter spaces. With gravitational confinement, the sun is so big, you can rely on gravity to hold the plasma together. The density it's very dense, 10 to the 4th times solid, relatively cool, a keV or so. And so that's about 100 million degrees. And then confinement time, 10 to the 5th years, meaning that's how long it takes for radiation to actually escape from the center of the sun out to the surface. So a very, very long time that you can hold this plasma together and give it time to fuse. With magnetic confinement, we're going to use very strong magnets to hold a very low density plasma together, make it very hot, 10 keV, and hold it together for seconds. With inertial confinement, what we do here is rely on the inertia of the target itself. And what we do is we compress our deuterium tritium up to very high densities, 10 to the 3 times solid, get it very hot. And because your density is so high and your temperature is so high, it means you have very high pressures, right? If you remember from high school chemistry or physics, PV equals nRT, right? So your pressures are huge, which means it wants to blow back apart, and your confinement time is very, very low, tens of picoseconds. Now, inertial confinement fusion, or ICF, can be achieved by using high power lasers to drive a spherical implosion. There are 2 main approaches to ICF. The first is called direct drive, on the bottom left. And what we do there is we're going to use an array of lasers to shine directly on a fuel capsule and use the laser energy to actually compress that capsule down and heat it up. Obviously, with this particular scheme, you're going to take laser energy and do direct conversion into kinetic energy. So you get a fairly high coupling efficiency and what we call reduced laser plasma interaction effects. And I'll explain what that means a little bit later. The other scheme is called indirect drive. And the idea here is you're going to have your fuel pellets sit in the middle of a little canister that we call a hohlraum. It's a German word for empty room. And your lasers, instead of shining directly on the capsule, now shine on the inside wall of this canister. And you convert the laser energy into X-rays. And then you use those X-rays to do the compression of the capsule. So this is a little bit like the oven that you have at home. You know, you turn on the heat and you kind of get more or less a uniform bath, right, of infrared to cook your meal. Here we're going to have a uniform bath of X-rays. So the advantages with indirect drive are relaxed beam uniformity and reduced hydrodynamic instability, because you're not using the conversion of energy to do that compression isn't quite as violent, and so you don't drive as many instabilities, basically. Now, in either case, after you deliver energy to your capsule, the reaction becomes the same. What happens is your shell ablates off, so blows off incredibly fast in a rocket-like reaction. And by conservation of momentum, we drive the rest of the capsule inward. If you do it right, your fuel core is going to reach 20 times the density of lead, and you get ignition at 100 million degrees Celsius, meaning your thermonuclear burn then spreads, yielding many times the input energy that you put in with the lasers. That is what we mean by ignition, more energy out than we put in. Now, the quest for inertial confinement fusion ignition has been ongoing for over 60 years, and a good proportion of that work has actually been taken on at Livermore. So ICF was born, the idea of ICF and early demonstrations in the late 1950s. The Ruby laser was invented in 1960, and legend goes that about the day after, John Knuckles, who was one of our former lab directors, figured out that you could use lasers to actually drive ICF. Knuckles' seminal paper came out in about 1973. And since then, Livermore has embarked on building a succession of larger and more energetic lasers, starting from Janus, Argus, Shiva, Nova, and through to NIF to today. And with these lasers, we've had a dual purpose. Not only fusion ignition, but also a lot of cool discovery science, because some of the conditions that you're able to generate with these lasers are similar to what, as Kim said, are similar to what we might have inside giant planets or inside stars. And so some very cool science to be done there. So at the National Ignition Facility, the NIF, we are building our own miniature sun. And NIF is the world's largest and most energetic laser to enable the study of extreme conditions for high energy density science. And as you can see, the building itself is enormous. It's the size of 3 football fields side by side, 10 stories tall, and housed inside are 192 separate laser beams. Each one alone is one of the most energetic in the world, and we combine 192 of them for a total energy of 1.9 megajoules and a power of 500 terawatts. Now, 500 terawatts is about 1,000 times the power of the entire US electrical grid. So how come when we fire NIF, your lights don't flicker at home? Well, what we do is we're going to take all that energy and compress it down into a very small amount of time, about 25 nanoseconds. The laser itself uses frequency tripled neodymium glass, which gives it a wavelength of 351 nanometers when it goes into the chamber, 3 omega or UV light. And if I take the roof off of the facility to give you a view inside, you can see that this enormous facility basically houses tens of thousands of optics that we use to actually amplify the lasers up to their full energy. And then what we do is we take all of that laser energy and focus it back down onto that tiny target. You can see on the top right a picture of the hohlraum, and then on the bottom right, a picture of the actual capsule held up to a human eye to give you a sense of scale. So you can imagine all of this laser energy in this enormous building getting focused back down onto this tiny target. So the NIF uses this laser-driven hohlraum to compress a fuel pellet of deuterium and tritium to achieve the conditions for ignition. The hohlraum is that cylindrical cavity. It's that X-ray oven. And you can see there that it's typically gold or depleted uranium. And it's about 1 centimeter in length, 0.5 centimeter in diameter. There's actually 2 holes on either end that we call the laser entrance hole. And the laser beams come in there, they hit that inside wall to generate those X-rays. The capsule sits right in the middle. It's about 2 millimeters in diameter. And you can see from this picture that there's also a fill tube that is inserted on one side. We use that fill tube to actually fill the capsule with the deuterium and tritium fuel right before the shot. Now, the fuel capsule itself is actually pretty complex. It is typically plastic, CH, high density carbon, basically diamond, that serves as the ablator surrounding concentric layers of DT ice and gas. And you can see here that the plastic, in this case, in this pie diagram, actually also has different layers of dopant. And what we do is we have to dope different layers with higher Z elements, so elements higher up the periodic table, and they can actually protect the DT fuel that sits on the inside. And the DT fuel takes the form of both a gas and an ice layer because we want gas in the middle to make it more compressible. It's easier to compress down. However, we have to pack enough fuel in there that we can actually get robust propagating burn. So we grow this little cryogenic DT layer. And what we mean by that is just like you grow water ice, this is just pure deuterium and tritium ice. And then the trick of inertial confinement fusion is to turn 100 million atmospheres of pressure into 300 billion via spherical compression. And so if you do it right, you see we use that bath with hohlraum X-ray radiation to do that compression and heating all at once. Through that compression, we take that 2 millimeter capsule and we compress it down to about 50 microns in diameter. That's about half the diameter of a human hair. And we need to stay as round as possible the entire time to make it efficient. So we're gonna attempt to play a video now to show you how all of this comes together. Let's see. And I'm gonna be talking over the video. All right. So we start in the NIF control room. This is where I, as an experimental physicist, actually spend a lot of time when it is my experiment. So first, the laser is going to be born in the master oscillator room. It is a fiber laser at this point, born at a nanojoule level. That's about 1,000 times less energy than your typical laser pointer. The laser pulse gets split 48 ways and goes into the pre-amplifier module, bouncing around several hundred times, getting amplified up to the millijoule level. So it's about 1,000 times up in energy. And then each beam gets split another 4 ways, gets expanded, and goes into the main amplifier, bouncing back and forth across this enormous NIF facility 4 times, getting amplified up to the kilojoule level. So that's another 1,000 million times up in energy. And at this point, we're going to follow a single beam. And you see now that each beam is about 40 centimeters by 40 centimeters. So this is huge. And the idea is there is so much energy in each of these beams. We need to spread it out over the optics as it's traveling through. Otherwise, it will actually damage the optics material itself. Now, half the beams are going to be sent up, half gets sent downwards. We are going to frequency convert from red to green to UV. And then these laser beams are now incident on that tiny target that's sat in the middle of that 10-meter target chamber. Half the beams come in from the top, half from the bottom, irradiating that inside wall, generating that very, very energetic flux of X-rays to ablate the shell and compress the fuel capsule. And this all happens over just tens of nanoseconds. And if we do it just right, we have ignition. More energy out than we put in with the lasers. So that is the name of the game. All right, let's go up. All right. Very excitingly, last August, a shot on the NIF achieved 1.35 megajoules of fusion yield, which is more than 70% of the gain needed for ignition. So you can see on that plot on the left, fusion yield versus year. Let's see, the NIF came online in 2009 and we started doing experiments immediately. So it's been about 12 years of experiments, and you can see our improvement over time to this shot that we had just about a year ago now. This shot used 1.9 megajoules of laser energy going in, producing that 1.35 megajoules. So that's why we would say 70% of ignition. This was a 25x improvement over where we were a year previous. What's really exciting is we're now firmly in this burning plasma regime. What that means is if, an analogy is if you strike a match, ignition is kind of like getting that flame to actually stick and grow and burn robustly. So that's what burning plasma means. With that shot, we also achieved capsule gain greater than 5. So we were able to get 5 times more energy out than got to the capsule. And then again, that's the laser gain of 0.7. And that's a definition that comes out of a National Academy's report from 1997. Now, this was spurred by advances in physics understanding, target designs, diagnostics, target fabrication, and the NIF laser. I will go through some of those advances in the next couple slides to explain how we got here. Now, this shot does mark a significant advance in ICF research and lays the groundwork for inertial fusion energy. The targets that we talked about, they're not just this little canister and a little ball that sits in the middle. They are a work of art, and they require microfabrication precision. So on the left is a picture of a gold-lined uranium hohlraum, and you can see that it's actually fairly complicated. There are all kinds of sensors attached to the hohlraum, cooling arms, because we have to hold it at very precise temperatures. The capsule, you can see it down on the bottom left as a diamond nanocrystalline capsule. It's again 2 millimeters in diameter and smooth to better than 10 nanometers. We really do care about every single little bump or divot on the outside surface of that capsule. We don't even, 10 nanometers is just a fraction of the size of a piece of dust. So even there's no dust anywhere in the system. And then on the right is a picture of the capsule. After we have grown the ice layer on the inside, what we actually have to do is take X-ray pictures of the capsule to look at the uniformity and smoothness of the ice itself as well. And then you can hopefully see on your screens with the contrast is good enough to see the little fill tube that we insert into the capsule. About 2 to 5 microns is the diameter of that fill tube. Again, a human hair is about 100 microns. So we're really talking about state-of-the-art microfabrication here. Now, a good fraction of our development and R&D goes into diagnostic innovation. And this is a really exciting area where we actually get to work with a huge number of collaborators, both inside and outside the lab as well, to develop new ways to measure the important parameters of our implosions with ever increasing resolution in space, in time, in spectrum. And so right now we have over 100 different diagnostics running on the NIF. Some of them are highlighted here. For example, when we generate those fusion reactions, those neutrons come streaming out, and we try to capture those neutrons to give us an idea of the yield and how uniform the hotspot was. And we do that with over 50 nuclear activation disks spread all around the chamber. On the right, we do measure the DT hotspot and field shape with both X-ray and neutron imaging from many different lines of sights so that we can reconstruct in 3D what the hotspot looked like. On the bottom right is an example of a hotspot electron temperature and measurement of impurities with a number of different X-ray spectrometers. And then right in the middle, we measure the hohlraum radiation flux, basically how hot, what the temperature is inside that little canister that we measure with a diagnostic that we call Dante. So it's a little play where, we're measuring the hellish-like temperatures inside that hohlraum. So the program has steadily advanced our physics understanding and the technology over the last decade to give us that improved performance. And now I'm going to walk you through the history of how we got to this great 1.35 megajoule shot. So again, on the left, I'm going to walk through the same plot you already saw, which is fusion yield over time, year. And on the right is a plot of hotspot pressure. So how hot and how dense that DT field got versus hotspot energy, how much energy we were able to couple in. And of course, we want to move to the top right of that plot to get to ignition. In fact, those dotted lines mark out an area where we have what we call yield amplification of 30 times. So yield amplification is, you start your fusion reactions going. What you're trying to do is actually trap those alpha particles, get them to redeposit their energy, and if they continue to heat up the plasma, and so you get this propagating burn. That's what we call yield amplification. So when you achieve about 30x, then we call this kind of robust ignition. And that's a parameter that comes out of theory and comes out of many, many simulations. So let's see, starting in about 2010 through 2012, we had what we called the National Ignition Campaign. This was the first time we were doing these very complex experiments on the NIF. We tried to do a type of implosion that kept us on a very low adiabat, meaning we tried to minimize the amount of entropy in the system to make the capsule as compressible as possible. We found out this was really hard. The capsule was very unstable. We had very high laser plasma interaction effects, meaning as soon as we turn the lasers on, you generate a plasma, and those plasmas then do crazy things. It will bounce your laser back out later on. It will absorb the laser energy in ways that you don't want. Because of that, we had very asymmetric implosions. We were not able to drive the implosion in spherically. And so we were only able to get 2.5 kilojoules back out of the implosion. Then between 2012 and 2015, we switched to what we call the high foot implosion. We decided to trade compressibility for robustness. So we said, okay, let's not compress as hard, and maybe it's easier to keep it round. And that worked. We had improved stability, and we improved our performance by an order of magnitude. Then after 2015 through about 2018, we switched over to what we call the high density carbon ablator. So instead of plastic, we used diamond. Diamond, being a more dense material, is a more efficient ablator if you can drive it with enough laser energy. And so what we would do is we shortened the laser pulse and just crammed a whole bunch of energy into the hohlraum really fast. Because of that, we had reduced laser plasma interaction effects. We also worked on reducing the size of the filled tube for that set of targets, and then found we had improved symmetry. And then that pushed us up to 55 kilojoules of energy coming back out. And then we switched to slightly even more advanced designs called the hybrid E or the IROM. So we changed the shape of the hohlraum a little bit and changed the relative size of the capsule, made the capsule relatively bigger inside the hohlraum. And if it's bigger, that means you're able to, there's more surface area to actually absorb drive energy. That's great if you're actually able to control the other degradation mechanisms. And over the 10 years of experiments, we had a better feeling for how to do that. And so that gave us improved performance, gave us improved compression. Our targets improved in quality with better fabrication techniques. And so you can see then on the right side, We are now very close to approaching that yield amplification band that we're aiming for in terms of hotspot pressure and hotspot energy. And so, spurred on by advances in target designs, diagnostics, targets, and the NIF laser, our progress really accelerated in 2021. We developed, well, we're always continuously building better diagnostics, and they're very important for us as our implosions get better to continue to be able to be sensitive to those degradations. Things that looked random before aren't necessarily, if you understand why they are, and our diagnostics help us to understand that. A key challenge was always targets. Even though they are technological marvels, real world imperfections such as pits, voids, the fill tube, shell non-uniformity were contributions to yield variation. And so you can see there on the left side, a picture of the pits on the outer surface of the capsule. You can't see them with the human eye, and definitely not. But what you could see on that pit and void detections plot kind of in the middle, we were able to bring down the number of defects per shell very significantly by over 2 orders of magnitude between 2020 and 2021. Laser variation also played a role, and we addressed that by making the laser more repeatable itself in what it put out. We went to this design that gave us symmetrically imploding larger capsules that absorb more energy. I talked a little bit about that already. And then we figured out through a combination of experiment, simulation, and theory how to maintain pressure at stagnation as those capsules were made bigger. Now, the NIF laser is absolutely a marvel, but in 2021, we undertook a number of different enhancement projects to allow the NIF to deliver the highest sustained levels of energy and power to date by continuously investing in optics and laser technology. So in the master oscillator room, that was the first part of the video that I showed you. Our team implemented new tools to actually give us better pulse shaping fidelity, meaning we could more precisely modulate the power output as a function of time, which is needed for our experiments. We improved the stability in the energy per beam that was coming out. And then also, not only is it important to diagnose what happens at the target when the laser hits the target, it's also important to diagnose what the laser itself is doing. And so the team implemented new diagnostics, laser diagnostics, to improve the reporting accuracy itself so that we had a better idea of what the laser was giving us. So 210808 combined a number of these changes and enabled a major advance. How much of an advance? Well, let me power through this slide. There we go, to show you what 0808 actually meant. So you can see that that pink bar is just growing. And you can see on the right side that with 0808, we landed firmly in that yield amplification of 30x range that we were aiming for. So another main takeaway of this was that over 10 years, we did only 171 shots where we actually used DT fuel in the implosion. So that just gives you an idea of how fast we were able to learn and how fast we were able to progress. Now, of course, each of these DT shots that we take is accompanied by a number of other experiments that we have to do, which we don't necessarily put DT fuel in the capsule to try to tune up the implosion. But really 171 shots was all it took to get here. And, of course, the amazing team and amazing laser, blah, blah. And the other main takeaway here is that the much higher pressure and energy that we saw in our implosion with very small changes to those input conditions indicate that we are in now a new regime of physics. So we've made much progress in the past few years, but a lot of work still remains to be done. So what are we doing next? We want to understand where we are. We want to assess the variability. We have actually taken a few repeat shots since 210808. And we varied a number of different things, the laser, the target, etc. And we're trying to understand the sensitivity to those input parameters now. We're also going to do shots where we dud the fuel. We don't necessarily use DT. We might actually put regular hydrogen in there so that we don't get burn. And it helps us to validate our models and understand simulations better. We also, of course, want to push to higher performance. We're going to do that with higher compression, higher laser energy, further improvements of the hohlraum, and then use the current design for science experiments on the NIF. Currently, the output from this implosion is the most powerful and energetic driver we have ever had for high energy density physics. And so it's very exciting, some of the very cool experiments we can now do. And of course, then improve our simulation capabilities through a combination of all these things. So really, this is a very, very exciting time for our field. Again, this was an accomplishment that built on decades of hard work and dedication by the community. We now have significant confidence that NIF is capable of ignition and higher yields. I already talked a little bit about the next steps. We also need to accelerate refurbishment of the NIF and recapitalize infrastructure. There is no other laser in the world that comes close to the NIF right now yet. However, the NIF itself is 20 years old. So things are, they're getting old and getting a little run down sometimes. So we do need to do a refurbishment of NIF. We'll continue to exploit the capability of burning plasma, of ignition, see what the limits are on NIF. We're also exploring an energy upgrade of the laser itself to expand the capabilities. And finally, inertial fusion is a path to carbon-free energy and should be explored. And so let's talk a little bit about that in the next few slides. These recent NIF results do establish the basic scientific feasibility of laser-driven inertial fusion energy, what we call IFE. And so when the news came out of our August 8th, 2021 shot, we got a lot of media coverage. It was really exciting. It was also really exciting to see the immediate extrapolation to fusion energy as the ultimate energy source, right? Now, of course, the NIF is not a power plant. There would still be a lot of parts that you can see on the right that we would have to actually put together to harness fusion energy. But what the NIF has done is demonstrated that laboratory ignition is possible. Before that, it was a huge question for inertial fusion energy in general. No, we achieved a gain of 0.7 with 0808. The key question for inertial fusion energy is, can we actually achieve gains of 100 or so? Just getting more energy out than you put in with your laser is a great first step, but it's not quite enough to actually both run a power plant, because you need to circulate that energy, and economically send energy out to the grid. So you need gains on the order of 100 or so. The concept for an IFE power plant includes the driver, in our case it would be the laser, a target chamber, a target factory, and a steam turbine to generate that electricity. And the other thing is, it is envisioned that we would have to repeat a NIF shot about 10 times a second to actually make the economics work out. Currently, the NIF shoots about once every 4 to 8 hours. That is by design. It's cooling time that we need for the lasers. But for a inertial fusion power plant, we would have to repeat that reaction 10 times a second at 10 hertz with much higher gains that we're currently having today with the target. So again, the NIF is a scientific exploration facility. It's very different from what would be needed for that IFE power plant. In addition to going from single shot to 10 hertz, an electricity producing power plant would also require a more robust high margin ignition scheme, high rep rate target injection and tracking. You need robust first walls and blankets, tritium processing and recovery, remote maintenance systems, and viable economics. So obviously it's a big challenge to make this actually happen. However, a number of promising technologies key to eventual IFE systems are already making steady progress. For example, laser architectures such as Livermore's high repetition rate advanced petawatt laser system are pushing the frontiers in driver technology. Happel's was designed, developed, and constructed by Livermore. It is the world's most advanced and highest average power diode pumped petawatt laser system. It shoots at 30 joules, 30 femtoseconds, giving us what we call a petawatt class laser. And it's also able to shoot at 10 hertz, the 10 times per second mark that we needed to get to. So you can see that, our technology is advancing along quite well. Now, the exciting thing, once you have these high rep rate lasers, is you can also do experiments at that same rate, right? So we're now developing what we call high repetition rate experiments on these very novel lasers, and with that lay a very critical technology development for IFE. Now, what's cool is, once you move to such high repetition rates, 10 hertz, that is faster than a human being is able to even, press the laser shoot button. And it is faster than we are able to save data manually and analyze data. So you have to start relying on high performance computing and start pulling in machine learning and artificial intelligence to able to run your laser system, run your experiment. And you can start to generate these, what we call loops, feedback loops between the laser itself and the experiment. So if you're collecting data at 10 hertz, you can analyze it in real time. You can see how to make your data better. You can see where the data is interesting, and you can steer your laser to a different parameter space to collect data where there are the biggest uncertainties or where the data is most exciting. To make that happen, we also have to develop a lot of supporting technologies. They happen to be core competencies that we have at Livermore. So this is a really exciting project where we get to pull in people from across the laboratory to make this happen. Now, the necessary milestones for inertial fusion energy would center around increasing gain, robustness, and repeatability to reach commercial viability. Because keep in mind, if we want fusion energy and to be a realistic energy source, it also has to compete with the other energy sources out there. Now, conceivably, there's a number of steps that are marked there in the 1, 2, 3, 4, 5 of successively larger and more complex facilities that we might want to build to demonstrate all these different technologies. The point is, this will require government investment, but this is also an opportunity for private industry to start getting into fusion. And we're actually starting to see a lot of new investment from venture capitalists and private companies. And so we're in a very interesting time and place right now as we see more people around the world get interested in fusion. So with the wider community, we are working to restart a funded, coordinated IFE program in the US. This NAS study that came out in 2013 basically said the appropriate time for the establishment of a national coordinated inertial fusion program for fusion energy program within the Department of Energy would be when ignition is achieved. And with the recent NIF shot, that is basically ignition. So this is the time. Nationally, there's been a lot of activity. We recently held a series of community and Department of Energy driven IFE workshops to help define a new national IFE program. And these workshops then bring the community together to lay out new research directions the government should undertake to make IFE a reality. And so I'll just wrap up here that the recent game-changing NIF results lay the groundwork to explore inertial fusion as a path for clean energy with the wider community. IFE will be a multi-decadal endeavor. It will require a lot of innovation. However, there's a number of promising technologies that are already making steady progress, many of them at Livermore. And fusion energy offers a long-term vision for enduring global climate and energy security. So thank you.
Thank you, Tammy. That was great. Especially appreciate how you walked us through where we've been, how we got here, where we are, and where we're going. Unfortunately, I don't think we have time for questions because we like to reserve a few minutes for our students to have a special interaction with Tammy. So what I'm going to ask our audience participants to do is, if you have a burning question, send it to info@livermorelabfoundation.org. We will make sure we get it answered and get it back to you. So with that, I really want to thank Tammy for today's talk. We hope that everyone enjoyed this talk. And if you did, assuming you did, that you'll join us again in 2 weeks on July 13th, when we will welcome Jay Davis to discuss sliding through disciplines and programs. He'll be sharing his perspective on how best to approach a STEM career at the lab. So with this, I would like to ask our current and former foundation students to remain on Zoom for their special Q&A session with our speaker, and thank everyone else for attending today. See you in 2 weeks.